Occasionally you have a reaction mixture and you want to know if the reaction mixture is going to proceed in the forward direction for the reaction of interest or in the backwards direction. There's two different ways to do this using two different formalism, one based on delta G and one based on K and Q. Let's look at the method based on delta G. So let's use an example here. Let's imagine that we mix some salts. Okay, so we mix a bunch of salts, we dissolve them in water, and at least initially, the concentration of sodium, dissolved sodium, and dissolved chloride is 10 molar. And we're interested in this reaction. We're interested in the dissolving of sodium chloride solid to form the aqueous ions. So the question is, if initially we have 3 molar of this and 10 molar of this and some leftover solid as well, which way does the reaction proceed? Does it go to the right or does it go to the left? Do we start precipitating more sodium chloride, or do we actually dissolve some of the solid to make more dissolved ions? So that's what we're asking. We say, do we go in the forward or reverse direction? Okay, now to figure out which direction we go, we could use delta G. We know if delta G is negative, then the reaction is going to proceed spontaneously in the forward direction. So we can write our expression for delta G. And then see if there's a way we could do this. Well, to do this problem, we would need Q, and we can get Q from our concentrations of our reactants, our products here. We would need delta G standard, and then we can calculate this. So let's see if we have delta G standard. We can imagine calculating delta G standard from perhaps from delta S standard and delta H standard, or we could calculate it from delta G as a formation, and those are covered in other screencasts. So anyway, let's imagine that this is just given. So we'll say that this was part of the problem statement, that it's given what delta G standard is for this reaction. And we look this up or calculate it, and we find that it is -8 kilojoules per mole. Okay, so the fact that this is negative doesn't mean that any particular reaction mixture is going to react to the right. It means what? Take for a minute to think about what a negative delta G standard means. Okay, it means that the reaction itself is product favored. So we should expect to see a lot of products when we get to equilibrium, but depending on how many products we already have, we might have to go left or go right. Okay, so this just says that the equilibrium lies to the right. In other words of saying is that the equilibrium constant for this reaction would be a number greater than 1. Okay, so let's use delta G standard and our Q to find delta G and see which way this reaction is going to go. Okay, so we've got a reaction, and we said we already knew that the delta G standard was -8 kilojoules per mole. Okay, and let's assume that we're working at 25 degrees C. That wasn't given in the problem statement, but we can't do the problem without it, so that would actually have to be given as well. Okay, so let's plug in our numbers here. So we say delta G is equal to delta G standard plus RT log of Q, and let's write our expression for Q. So Q is products over reactants. So we've got concentration of sodium, concentration of chloride. And neither one of those has a coefficient, so we don't have any exponents here. So for solids or liquids that are pure, we just plug in a 1 down here. So often we'll omit this since we're just dividing by 1. At this stage, you might be wondering, how can I take the logarithm when I've got units in here? This is units of molarity squared. What's the units of molarity squared with the logarithm taken? Well, in actuality, what we're really plugging in here is the ratio of the concentration divided by the standard concentration. So since the standard concentration is equal to 1 molar, we'll just write that here as a reminder. We're taking the concentrations here, and whatever that number is in molarity divided by 1 molar, this ends up being a unitless number. So really this is a logarithm of a collection of unitless numbers, and so this Q has to end up being unitless as well. So that's actually not a problem. Okay, let's plug in the numbers. So we said delta G standard was negative 8,000 joules per mole. And of course, this is an opportunity to make a mistake because this is going to come out to joules, and so if this is in kilojoules, you'd better convert it first. Okay, and then R, 8.314 joules per mole per Kelvin, times T, which we said was 298 kelvins. So remember in thermodynamics, whenever it's not a temperature difference, but an absolute temperature, you've got to use kelvins and not degrees C. All right, then we take the logarithm, and we have the concentration of sodium. If we look back at the problem statement, that was 3 molar, and the chloride was 10 molar. So we've got 3 times 10. So that's the unitless concentration, right? It's the concentration divided by 1 molar. Okay, great. Let's go ahead and plug in the numbers here. And we end up, once we take the log of 30, multiply it by this, multiply it by that, we end up with delta G coming out to a positive 400 joules per mole. So not very positive, but still positive. So we started off with a negative delta G standard, and yet because this term was so positive, we ended up with the overall delta G being positive. So the reaction is going to go to the left. It's going to go this way. So if we look at our reaction, just draw an arrow up here, we're going to go this way. We're going to precipitate sodium chloride. Okay? So why is that so? Why is it that we have a negative delta G standard and yet we're going to go backwards? Well, it's good to look at this as sort of a graphical G-plot, I think is helpful. Your professor has probably drawn one of these for you in class, where you have products and you have reactants, and then Q tells you how far along you are in your reaction progress between reactants and products. And the reaction we did just now has a very negative delta G standard, and that's this number. The difference between pure products and reactants. Okay. But if we look at G itself, as we progress from products and reactants, it sags below. Why? Because of the entropy of mixing. Because any place in here where you actually have both present in the same vessel, you're going to have some entropy of mixing, and that decreases the overall Gibbs energy. So systems tend towards minimum G values. So that means if you're over here, you're going to go this way. And if you're over here, you're going to go this way. So if we look at our problem, where were we? We had these very, very high concentrations of chloride and sodium. So we had really high concentrations. So we were really far over towards the right of having a lot of product. So we were, say, here. I'll just draw a little dot and say we started off here. So to get the minimum Gibbs energy, we actually had to go backwards. Okay? So even though it's overall energy downhill to go from these reactants to these products, if you start where that green dot is, you're going to react backwards because the equilibrium spot, the spot where you're going to end up, is right here because that's the minimum Gibbs energy. Okay, so that's an example for finding which way a reaction progresses using delta G. In a separate screencast, I'll show you how to do it by comparing K and Q.